All right, guys, we're coming up to time that we need to do a review for our proximity sensors test. So let's get right into it. So we'll start off with some general questions. So the first question for you guys is, what's the difference between an analog and discrete switching sensor, and which circuitry component makes the difference? So this one right here, where it says 1.3, I'm referencing the Allen Bradley sensor manual that you were given in class. There is a digital copy, so if you look in the comment section below, you will be able to download a digital copy to your phone. But that one is chapter 1, page 3. You should be able to have the answer for these guys, and I'll do the same for any question where there is a reference in the Allen Bradley sensor manual. So the difference between analog and discrete switching. Well, discrete switching, we found most of the sensors that we were working on were discrete switching. Either they were on or they were off. They had 0 volts or 24 volts DC as the output. We weren't hooking these up to the PLC yet. We were hooking them up to an LED, but the LED was a 24 volt DC LED, and when the sensor conducted, then the LED obviously turned on. So discrete switching is just basically on or off. Then we found that with the, the M12 analog inductive sensor, we had an analog output. And that guy actually had both a 0 to 10 volt DC or a 4 to 20 milliamp DC output. We couldn't take the two values at the same time. We're either looking at the voltage or looking at the current, but those are two standard values that would be going into our PLC. 0 to 10 volts DC as the voltage output, or 4 to 20 milliamps as the current output. Each PLC will have either a 0 to 10 volt signal, like that comes in, like some S71200s just come like out of the box with a 0 to 10 volt analog input. It doesn't have a 4 to 20 milliamp input. Others will only have a 4 to 20 milliamp input. Others, like ours, where we have the additional analog I/O on the side, you can have either a 0 to 10 volt signal or a 4 to 20 milliamp signal. In our Siemens TIA, we're toggling those analog inputs to be either voltage or current within the software. Others will be a dip switch, where you change the dip switch and it changes from voltage input to a current input. But those are our standard values. The component that allows us to change from an analog to discrete would be, and I love saying this word, this is the Schmidt trigger. So the Schmidt trigger is right here, and this guy is the one that allows us to give on or off outputs. So this one we have an inductive sensor here. So we have a tank circuit here with the capacitor and a coil. We can tell that this is an inductive sensor because the front face of the sensor has a coil emitting a magnetic field thousands of times a second. And the capacitor dumps its current towards the coil, creates a magnetic field, then the magnetic field collapses, back feeds, and charges up the capacitor. That voltage is sent into the op-amp. If there's any difference between that voltage and our reference voltage coming from this voltage divider here, then an output comes out. The Schmidt trigger is looking for discrete upper and lower values to turn on and to turn off. So this value, this guy right here, this component for the Schmidt trigger, that's the one that allows us to have on or off outputs. If we wanted to have an analog output, then we would remove that trigger from the circuitry, and then that signal would go straight to the base of the transistor and slowly open it and closing it, allowing us to have a variable output, either 0 to 10 volts output or 4 to 20 milliamps output there. So the Schmidt trigger is the one that allows us to have discrete switching on or off. Okay, next question. Sensor has 3 leads. Identify the colors and their corresponding uses. So I said review the notes from the class. It's interesting that the Allen Bradley manual is phenomenal, showing us all the different types of sensors, but neglects to show us the wiring or the colors. It's very strange why that is missing from the manual. So from our notes that we've been taking in class, then the colors for these guys on a 3-wire. Now again, there's 2, 3, and 4-wire sensors out there in the field, but the one you're going to see the most is a 3-wire. So the color for those guys is brown for the positive, blue for the negative, and black for the output. So we need to provide these sensors with 24 volts DC, right? So brown is the positive, blue is referencing 0 or negative, and black is the output going to the PLC. So they'll always have load here. The load is the PLC, like this thing right here. That is the PLC, okay? The switch is a transistor, but oftentimes they will show like a single pole switch, just to simplify things. This one is called a sourcing sensor, in that it is providing a source of positive current to the PLC. there are a number of little tricks here that we can figure out. This arrow right here is pointing in. So when you look at PNP, it's pointing in. Arrow is pointing in, pointing in. It's a PNP. The first letter in PNP tells you exactly the polarity that it is switching. So it is switching the positive, being P for positive, right? That positive is coming in into the transistor, switching the positive and providing that positive current to the PLC. The PLC already has a reference to the negative of the power supply here. Okay, again here, positive going into the switch, the PLC already has a reference to the negative there. Now I'm going to switch over to the NPN. Watch, the color code is going to be exactly the same on the NPN. So here for the NPN, we have brown for the positive, blue for the negative, and black for the output here. Okay, this one is an NPN. The arrow is not pointing in, so the trick here is not pointing in. So if the arrow is not pointing in, it is an NPN. What is it switching? Well, the first letter is telling us what it's switching. It's switching the negative of the power supply. Okay, so here we can see that the brown is the positive going into our sensor. The blue is the negative, so we provide it with 24 volts DC. But in order to look at whether we're switching the positive or negative, we need to look at this image right here. So this is our load, or the PLC. It already has a jumper between the common and the positive, so it's already referencing the positive, and the switch, being the sensor, is syncing that positive current back to the 0 volts terminal there. Okay, so an NPN is called a syncing sensor, in that it is syncing that positive current back to the negative. But it doesn't matter whether you're looking at a PNP or an NPN, the color code is always the same. Brown is the positive, blue is the negative, and black is your output. Okay, excellent. Let's take a look at the next thing. I guarantee you I'm going to give you one of these diagrams here where you have to tell me whether it is a PNP or an NPN sensor. There is no transistor there, so we can't see whether it's pointing in or not pointing in, so we have to look at the load. So let's take a look at the load right here. We can see here that from our power supply, we're providing positive to the brown and negative to the blue, so we're providing 24 volts to the sensor here. And the black is the output here. But it looks like the PLC is already referencing the positive of the power supply here. So we already have a reference to the positive. Looks like we are switching the negative, right? So we are syncing that positive current here through the sensor to the 0 volt terminal here. So this one is most likely an NPN, or a syncing sensor. Okay, hopefully you followed there. Let's do another one so that we're a little bit more confident in this. Okay, so we're looking here. This is the load, this is the PLC. Looks like the sensor has positive and negative. It's being provided with 24 volts DC. The black is the output, right? Brown is the positive, blue is the negative, black is the output. The PLC, though, is already referencing the negative. So the common is jumper to the negative here. So then we must be switching the positive to the PLC. So we are providing a source of positive current to the PLC. So this one is a PNP switch. Okay, need to have at least 3 or 4 times looking at this, so let's look at another one. So this one has the PLC, so this is our PLC over here. This is our sensor wiring over here, and there's our 24 volts DC supply. So a little bit convoluted, but we'll figure it out. It might be easy if Pete forgets to white out the answer here. So the answer is that this guy is a PNP, or sourcing sensor. Okay, why is it a sourcing sensor? Well, because let's take a look at the power supply here. We have positive to the brown. We should have negative to the blue. Okay, beautiful. That gives us 24 volts to the sensor. Then the output is the black wire, like we've seen before. And going into the PLC, we have to look at the common. The common looks like it is jumpered to the negative here. So the common is already referencing the negative. So we are switching the positive. So you can see the positive comes through the switch and into the input of the PLC. So this one is a PNP. We're switching the positive of our power supply. Okay, to mess you up even more, we have 2 different terms here, sourcing and syncing. The switch itself is providing a positive source of current. So it is a sourcing sensor. The PLC input, though, is a current syncing input, right? So if your sensor is sourcing, then your input is syncing. Okay, then it goes in, basically goes to an optical isolator and fires on the input of your PLC there. Okay, hopefully you're not totally confused at this point. Let's take a look at another one. So this one here, we have brown is the positive, so brown is referencing the positive. Blue should be referencing the negative. Yes, that looks good. Black is the output, but let's take a look at the PLCs. Remember, this is the sensor, this is our PLC input, and we're looking at the common. The common looks like it is referencing back to the positive. So the PLC already has a reference to the positive here, so we must be syncing that positive current through the switch and back to the negative of the power supply here. So this one is going to be an NPN or a syncing sensor. Again, if we have a syncing sensor, then we have a sourcing input on the PLC. Okay, again, as we sync that current back, then it will go to the optical isolator and fire on 5 volts into our PLC input there. Okay, so I'm going to give you one of those diagrams. You have to tell me whether it is a PNP or an NPN. Oh, looks like there's even more. Okay, let's take a look at this guy. So this one again, we're looking at whether it is PNP or NPN. We're looking at a number of things. We're looking at where the positive is. So positive goes in here. The negative goes here. So that's our 24 volts power supply for the sensor. Black is going to be the output to the load, which is PLC. And we're looking at what the PLC is already referencing. The PLC looks like it's referencing the negative. So the switch or the sensor is switching the positive to the PLC. So the first letter is telling us what we're switching. So this is going to be a PNP sensor. It's providing a source of positive current into the PLC. The PLC already has a reference to the negative here. Okay, I may give you a 2-wire or a 3-wire diagram. I'm probably going to give you a 3-wire, but just to show you the 2-wire sensors here. Let's take a look. We have our 24 volt power supply on this side and on this side. The NPN is switching the negative. So the PLC, this box right here is the PLC. It's already referencing the positive, and the switch is syncing that positive current through the switch and back to the negative here. Okay, it's switching the negative. For a PNP, it's switching the positive. 24 volt power supply, there's our PLC. The PLC is referencing the negative, and the positive is going through the switch and over to the PLC input there. Okay, so it doesn't matter whether we're looking at 2-wire or looking at 3-wire. The color code is the same in that we don't have actually the color code is different, right? This one is brown and black. On the 3-wire, the output was the black there. So be careful on the wiring here. Okay, let's take a look at the 3 and 4-wire. The 3-wire, like if I give you this diagram right here, I'll hopefully have whited this out so I don't give you the answer. But this one here, the box is the PLC. The PLC is already referencing the positive of the power supply, and the switch is switching the negative and syncing it back to the negative there. So this is a syncing sensor or an NPN. Okay, if we take a look at this guy right here, this one is a PNP. So there's our PLC. The PLC is referencing the negative already, and the switch is switching the positive and providing a source of positive current into the PLC. Okay, same color code, brown for the positive, black for the output, blue for the negative. Okay, same whether it's a normally open or normally closed output. The only difference between a 3-wire and a 4-wire is that the 4-wire has both a normally open and a normally closed output. So here on the NPN here, the black is going to be the normally open and the white is going to be the normally closed. Over here again, the black is the normally open and the white is the normally closed. The power supply for the 24 volts, positive to brown, and negative to blue. Okay, so that seems to stay constant all the way through. Okay, so hopefully you're cool on the 2, 3, possibly the 4, but I'm probably going to give you just the 3-wire, and you're going to tell me whether it's an NPN or a PNP. So center in on the 3-wire and make sure that you're cool with those guys. Okay, what's the differential travel property or the hysteresis of a proximity sensor? So on the analog sensor and on the discrete sensors, we saw that there was a hysteresis. There was like a difference between where it turned on and where it turned off. So particularly with the digital outputs or the discrete outputs, for the inductive and the capacitive sensors, the hysteresis or the difference between the turn on and turn off point was like a 0.5 mil to 1 mil difference between the two. That's just so that if something's vibrating, that it doesn't turn the switch on and off, on and off, on and off as it vibrates. So they're always going to have to be closer to turn on So here we can see here that the object is closer to turn on and farther away to turn off. With the inductive capacitive sensors, the hysteresis, or the difference between those 2 points, was like a 1/2 mil to a mil difference. For the light sensors, so the photoelectric sensors, it was like, could have been up to like 10 or 20 mils difference between your switch on and switch off points. But the hysteresis is the difference between where you're turning on and where you're turning off. Okay, again, referencing chapter 4, page 10 of the Allen Bradley manual. Okay, let's take a look at some more of the inductive proximity sensors. So with these guys, I'm going to ask you which component gives you short circuit, overload, transient noise, false pulse, and reverse polarity protection. So I centered in on these 3 protections right here within the circuitry. So short circuit, over voltage or transient noise, and reverse polarity protection. And so taking a look at this diagram here, let's take a look at the short circuit first. So in line with the transistor, there is an RTD. The RTD is going to limit our current here. So as if we hooked up too large of a load here, then it would pull too much current, and an RTD is usually used for temperature sensing. But we know that it has a positive temperature coefficient, so as it heats up, the resistance increases exponentially. So if we have too much current in that we've hooked up too large of a load and we're going to smoke that transistor, then hopefully that current heats up the RTD, its resistance skyrockets, and it limits the current, so hopefully we can save that transistor before it blows. You can't troubleshoot any of these guys. They're all hermetically sealed and encapsulated in plastic, so there's no way you can fix this. You would basically have to throw it out if you smoke that transistor. So that's going to cover the overcurrent. Okay, if we have over voltage, like a spike that comes through from a drive that turns on, or a dimmer that's going, or a magnetic field from a motor that just collapsed, then it creates a spike of voltage. Well, a zener is there so that it shorts out this transistor or bypasses the transistor. A zener in forward bias normally acts as a diode, but if you put it in reverse bias, it acts as a voltage sensitive switch. So if the voltage gets too high, then this guy starts to conduct and it bypasses the transistor, again, hopefully stopping that guy from being smoked. So overcurrent, transient noise or over voltage, and then reverse polarity. So you're going to put the positive to the brown and the negative to the blue, but why are you doing that? Why can't you just put positive and negative here? Well, that's because the transistor itself needs to have a certain polarity in order to work properly. So it has a little diode right here for reverse polarity protection. You have to put the positive to the anode and the negative to the cathode in order for this guy to work. Okay, let's take a look at this one because this one's a little bit more convoluted. Is this one a PNP or an NPN? Well, let's take a look. This one is the output load, right? That's the PLC. Looks like the PLC is already referencing the negative, and it looks like we are switching the positive to the PLC. So this one would be an example of a PNP sensor. Okay, so the 3 components are the RTD, the zener diode, and the diode, providing with all that protection. Excellent. Let's move on to number 10. How does a metal object reduce the amplitude of the oscillating circuit? So what happens is that as the piece of metal gets closer to the front face of the sensor, then it stops the oscillator circuit. The oscillator circuit, if we go back, that is this guy right here, the tank circuit, where it oscillates back and forth between these guys thousands of times a second, creating magnetic field on the front face that goes out thousands of times a second. If you put a piece of metal in front of there, then that magnetic field cuts across the metal of the object that you're trying to sense, creates little eddy currents on the front face of the metal there. Those eddy currents have their own magnetic field, which screws up that circuitry. So it's basically little eddy currents that are created or induced onto the metal that you're trying to sense. And what does it do? It stops the oscillator and then stops the output or toggles the output of the unit, depending on whether it is a normally open or normally closed output. Okay, number 11, when would you use an inductive proximity sensor? Anytime you're looking for the presence of metal. So here we are looking at different cans going by with the inductive proximity sensor on the side here. Here, this is from a t-shirt factory, so as it moves back and forth, then this piece of sheet metal goes in front of the inductive sensor and tells it that it's at that position. And here, if we're looking at rotation of something, then sometimes we might have a cam, And say this cam has like 16 different ridges here, then every time that the piece of metal comes in front of the inductive sensor, it gives a count, and we know that 16, in this case, 16 counts equals 360 degrees of revolution. So we can keep track of where we are in the revolution or how many revolutions we've actually made on the machine. So basically, anytime you're looking for the presence of metal, you will use an inductive sensor. Okay, which inductive sensor has a longer sensing range, the M12 or the M18? Well, the 12 and the M18 is telling you the distance of the diameter of the front face of the sensor. This is 12 mils, this is 18 mils. There's a coil that's in there. So you have a smaller coil or a larger coil. Which one do you think is going to have the longer sensing distance? Well, the M18 is definitely going to have the longer sensing distance because it has a larger coil on the front face of the unit. This one we saw for our class had 6 mils of sensing distance. This one had a maximum of 8 mils, so it's not like we're talking about inches difference. We're literally talking about 2 mils difference between the M12 and the M18. Okay, later on I'm going to ask you about shielded versus non-shielded. This one is an example of a shielded sensor. The threads go all the way to the end. This is a non-shielded sensor. This is a non-shielded M18. This is a shielded M18. How do I know it's a shielded? Because it has threads all the way to the end, so I could flush mount that in a piece of metal. This one does not have threads all the way to the end, so there's no way that I could flush mount that. This would poke out of the side of the conveyor and not be flush mounted on the piece of metal. Okay, but the question is, which one has the longer sensing distance? The M18 is going to. Here's a chart showing the M8, the M12, the M18, and the M30, so standard sizes of sensors, and we can see that it progressively gets larger in the sensing distance. You can't see very far with these guys though. Like look, this is an M30, so the maximum we can see is 30 mils. So if you want to see farther, you're going to have to use an ultrasonic or a photoelectric sensor. Okay, number 13, what's the IP rating of IP65? So these guys are hermetically sealed. Like if we take a look at the sensor, it's all encapsulated and there's very little dust or debris or liquids that can get in there. But how much is it impervious to either dust or water? That's the ingress protection or the IP protection. So the first letter is telling us how much dust can get in there. So if it's 6, it's dust tape. No ingress of dust for 2 to 8 hours. So basically no dust is getting in there. The 5 is for water. So can you submerge it? Can you not? Can you splash it? Let's see. Number 5 is protected against jets of water, limited ingress permitted. So little splashes of water, no problem, right? So dump your coffee on it, probably okay. Submerge it over time, then that water is going to migrate in and short out the actual unit. So, but the ingress protection is your IP rating. The first one tells you the amount of dust that get in there, and the second one tells you how much water can get in there. Okay, what's the difference between shielded and unshielded? That's what I alluded to before. So a shielded sensor is something where you're going to be able to flush mount that in a piece of metal. An unshielded sensor is probably the one that you're most likely going to use. So a shielded sensor looks like this, right? So the threads go all the way to the end. So I could flush mount that in a piece of metal. So that would mean that I would have to make sure that the magnetic field was only on the front face of the sensor. On this guy, the magnetic field goes out and around to the side. So I can't flush mount this guy because if I put a piece of metal here, then it will trip off the sensor without anything being in front of it. So the threads only go to this point right here. If we go back one slide, you can see that there are 2 shields right here, and they center the magnetic field on the front face of the unit. It's not being depicted properly here. This one right here would have a smaller sensing distance than an unshielded. So this is an unshielded sensor, so the magnetic field goes out and all the way around to the side. This one would have a longer sensing distance. This one would have a smaller sensing distance. This one you cannot flush mount in metal. This one you can flush mount in metal because it has these 2 shields that suck the magnetic field into the front face of the unit. Okay, so most of the time you'll be using an unshielded sensor. Okay, number 15, what's the maximum sensing distance for an aluminum object if the nominal sensing distance is 10 mils? So I've used a multiplier of 10 mils there to make it easy so we don't need to have a calculator for the test. There are other sensors out in the field now that don't have these correction factors, but oftentimes if you're using inductive proximity sensors, then there will be a correction factor for different types of metals. So we can see here that for mild steel, we're going to get 100% of our sensing distance. Stainless steel, we're only going to get 85. Brass, we're going to get 50% aluminum, we're going to get 45% of our sensing distance, and copper, we're going to get 40% of our sensing distance. Okay, so if I have a 10 mil maximum or nominal sensing distance and I'm looking at aluminum, then I'm only going to get 45%, or I should be very close to the sensor. I need to be within 4.5 mils on the sensor for it to accurately, catch that piece of aluminum going by. So there is a correction factor for different types of metals. Okay, let's take a look at some capacitive proximity sensors. So number 16, when would you use a capacitive proximity sensor? So you could use it for looking for metal, but you're probably going to use an inductive sensor. So applications would be something like this: liquid level sensing, bottle filling, checking for material in a package, and plastic part detection, right? Also for liquid flow as well. So here we're just keeping track of the bottles as they go through. And so you can see the top here is being picked up by the capacitive sensor. It's not over here and picking up every bottle, so this is probably just keeping track of the fact that the line is still moving. Okay, this one here is looking at the level inside of the tank. The cool thing about capacitive sensors is that there's a potentiometer on the back, and you can increase or decrease the sensitivity. So I can decrease the sensitivity so it does not see the plastic or the glass of the tank and only sees the liquid inside. Same here for the flow. I can reduce the sensitivity so it doesn't see the plastic hosing, it only sees the liquid inside. Okay, or if I'm looking at for liquids inside of a milk carton, I mean, the capacitive sensor would have to be basically very, very close to the actual unit, but it could see through the cardboard and see the milk inside because the milk has a higher dielectric. Okay, you'll see this if you purchase a new car. Capacitive sensors, you're seeing it on your cell phone. Capacitive sensors are used everywhere. When you go up to your new car, you basically, if you have the key fob in your pocket, then when you grab the handle of the car, then you change the capacitance of that circuit. Okay, this one, which type of proximity sensor is depicted below? Okay, well, first of all, let's see whether this is PNP or NPN. That's not the question, but let's take a look. So here we have positive to the brown, we have negative to the blue. This is our black as the output. This is our PLC, and the PLC, it looks like it's already referencing the positive. So this would be an example of an NPN sensor, or a syncing sensor. PLC already has a reference to the positive, and we're syncing that positive current back through to the negative here, because there's the switch right there, right? So positive to the PLC, and we're syncing that through the transistor and back to the negative there. What type of sensor is it? Well, we've got to look at the sensor face right here. And there's a C there, so this one is a capacitive sensor. You can see that the two, similar to the one where we had the coil here for the inductive sensor, the two plates of the capacitor are normally on top of each other, but they have been opened up like a sandwich, and the inside, or the dielectric, is going to be air, and then if we put something in front of the sensor, it will change from a dielectric of air to plastic or metal or whatever we put in the front face here. So this is a capacitive sensor because we can see the two plates of the capacitor, and whatever is in the front here, that's going to be the dielectric. Okay, so we can answer a number of things there being NPN, or we can look at the fact that it is a capacitive sensor there. Okay, so let's take a look at the next question here. How do you adjust the sensitivity of the unit? Well, there is a potentiometer on the back of the unit, the smallest potentiometer ever. And so on some of the units, we've seen that like class over class have used these guys, and they basically like stripped the back end of the pot. But you use a slot screwdriver, the smallest screwdriver known to man, and then you can change the sensitivity of that sensor. And by doing so, then that answers the next question on what application would you make use of the sensitivity adjustment. And again, referencing the Chapter 5, page 6 of the Allen Bradley manual, that we're looking at liquid level sensing. So we can negate the wall of the tank and look on the inside of the tank here. There are limitations though, like this one, there's a glass wall with the dielectric of 3.7, so that's fine if the alcohol on the inside has a higher dielectric, because we can reduce the sensitivity so it no longer sees this dielectric, only sees this guy. But if we had flour in there, there's no way that this would work. Because if we reduced it to not see 3.7, there's no way we're going to pick up the flour within a dielectric of 1.5. So there's obviously limitations in that whatever is inside of the container has to have a higher dielectric than the box or the container that it's in. Okay, a couple questions here for 20 and 21. When a non-conductive or like a plastic target is within the sensing range of the capacitive proximity detector, we said that that is changing the dielectric. So it changes the dielectric, and by changing the dielectric, then it increases the capacitance of the sensor. Capacitive sensors can also look at conductive targets or metal targets. And so if a conductive or a metal piece is placed in the front face of the unit, it's not necessarily changing the dielectric, it's becoming another electrode of the capacitor. So think of it as increasing the surface area of the plate of the capacitor. Both of those guys are increasing the capacitance. That op amp is seeing that change in voltage and then firing on the transistor. So both of them, the previous one was the dielectric changes for 20, and for 21, the object becomes another electrode. Both of them increase the capacitance. Now, ultrasonic sensors. So I have not been able to purchase ultrasonic sensors yet, so we haven't wired these guys up, but let's go through the basics of these guys. One thing to know with ultrasonic sensors, so these guys are ones that send out an ultrasonic sound wave out, it bounces off the object, it comes back, but with ultrasonic sensors, there's always a blind zone. So in the front face of the sensor, for like an inch or two, you won't be able to sense anything. That's because the sound goes out and comes back too fast for the sensor to actually see that echo or the transmission back to the sensor there. So ultrasonic sensors are awesome. You can see a large distance from the ultrasonic sensor. The only drawback for the ultrasonic sensor is that right in the front face, there's a small blind zone on the front face of the unit because from what I understand, the sound goes out and comes back too fast for it to pick up. 23, describe how an ultrasonic sensor works. So again, we're referencing chapter 6 of the Allen Bradley manual. So basically it sends out an ultrasonic sound wave, bounces off the object, and it comes back, and it looks at the transmission time because it knows the speed of sound, and it just sees how long that sound wave took to go out and come back to the receiver. Okay, which materials are difficult for an ultrasonic sensor to detect, and why? Well, this guy's punching out a sound wave, so anything that's not a solid object, like foam, would be a poor thing to use an ultrasonic sensor. Bubbles or like a froth that happens on the time. So say you have a tank and you have an agitation of the top of the tank and a froth then develops on the top, or that would suck for this ultrasonic sensor because the bubbles would absorb some of the ultrasonic sound wave. If you have a froth on the top or bubbles on the top of the liquid level there, then you would use the one that goes at a different frequency. You use a radar sensor instead of an ultrasonic sensor. So anything that absorbs sound waves would not be a good application for an ultrasonic sensor. Okay, let's take a look at the photoelectric sensor. So we did a number of labs with these guys. These ones have an LED that punches out a light wave that goes out, bounces off the object, and then comes back to a phototransistor, and then that changes the output of the switch. There was 3 types of photoelectric sensors that we looked at, and again, if you're reading up on this is chapter 7 of the Allen Bradley sensor manual. So we had the first guy. There was 2 names that were used in different textbooks: transmitted beam or opposed sensing. That's where the transmitter and the receiver are in different housings, and if you put an object in the way of the transmitter, then it's going to trip off the sensor. So this one works when the light is broken. So transmitted beam or opposed sensing. This one has a long sensing distance. So if you're doing like a fire alarm system and you have an atrium where the smoke can travel from one floor to the next, then you'll put in a transmitted beam sensor so that as the smoke migrates up through the atrium and tells you that there's a fire on another level, then it will block that light traveling from the transmitter to the receiver and trip off the smoke detector. Okay? Other applications are for like if you're doing packaging and everything, then they'll use a light beam, and depending on the number of LEDs that are cut, it can tell you the size of the actual package there. This one's just keeping track of units as they come through. And this one is the light curtain for safety, right? So if somebody breaks the light curtain, then the machine stops as fast as possible and goes to a 0 energy state. Okay, other examples of the through beam, and again on the test I'm going to give you a bunch of different diagrams like this, so you have to tell me what type of sensor it is. Well, it looks like a light sensor. There is a transmitter, there's a receiver on the other side, and every time these guys come through, they're going to cut through the light and give us a count for each unit that's going through. Okay, the second type of photoelectric sensor was the retroreflective sensor. This is the one that has the transmitter and the receiver both in the same housing, and then it had like a 3M reflector on this side. So the light goes out, bounces off the reflector, and comes back to the receiver. And again, this one changes state when the light is blocked. So the light is always going through the reflector. When that light is blocked, then it changes state. Okay, some examples. So here we have the retroreflective sensor. How do we know it's retroreflective sensor? For one, it's on an angle like this, and then you can see the reflector on the back there, sending that infrared light back to the receiver here. Okay, the third type was the diffuse sensor. So all the previous ones change state when the light is blocked. This one changes state when the light actually gets back to the receiver. So if there is no object in place, then it's always transmitting a light out, but no light is getting back to the receiver. This one is a diffuse sensor, so the light goes out, and the diffused light from the object comes back to the receiver. Once the receiver sees enough light, then it changes state. Okay, so we have three different types. We have the transmitted beam, or opposed sensing. We have the retroreflective, and the diffuse sensor. Okay, and again, the diffuse sensor works in that the diffused or reflected light comes back to the receiver. Okay, what two types of operation are there for the photoelectric sensors? So we have light operate and dark operate. So light operate, the sensor is turned on when it sees the light. Dark operate, the sensor changes state when the light is broken. 27, why do these sensors make use of LEDs? So the beauty of an LED is that it doesn't have a filament, so the filament's not going to break. And you can turn those guys on and off thousands of times a second. You can also crank the current to them, and as soon as they're going to blow up, then you can stop the current to it. So they're pretty resilient. You can get them super bright, and then as soon as they're going to pop, you turn it off. Super bright, and then turn it off. And you can do that thousands of times a second. If you use a filament from a light bulb, then bing, that would definitely blow within a couple times of trying. So a couple thousand times a second, it can punch out that light. This one is kind of asking the same question for 28. Why are there two reasons that the sensor makes use of light modulation? Well, that is the fact that you're looking at a specific frequency of light. So around us we have, ambient light from the sun, or we've got ambient light from our LEDs, or we got ambient light from our fluorescence or our high bay lights. So those guys are all punching out different frequencies. These sensors are set up so that the LED is turning on and off a specific frequency that totally negates any other frequency from your ambient light. So the beauty of using light modulation is that you can turn the LED on and off, and you're looking for a specific frequency back. It's not going to change state until it sees that frequency. Okay, what advantage do polarized filters provide for photoelectric sensors? So in addition to looking for a specific frequency, you can also have filters so that if you're using a retroreflective sensor, then the light is going to be depolarized by 90 degrees. So you will put a filter in right here so that the light goes out, bounces off the reflector, it's depolarized by 90 degrees, and your filter is looking for, the transistor is looking for a specific frequency, and the filter will only allow that type of light to get through. So if you wanted to be deadly accurate, you would use a polarized retroreflective sensor. Okay, this one's a little bit trippy, but you can see here that the light is going out, hitting the reflector, and then changing by 90 degrees to come back, and the filter is only allowing that polarized light to come through. Okay, let's take a look at some applications now that we've taken a look at each of the different types of sensors. So this is what the bulk of the test is going to be. I'm going to show you a diagram, and you're going to tell me what type of sensor is being used for that application. So it looks like we have a cam here that is metal. this guy is sensing the presence of metal. So when given these options, capacitive, diffused, opposed, retroreflective, ultrasonic, and inductive, then the one on the previous slide is an inductive sensor. Okay, this entire test is multiple choice. So be careful in transferring your answers to the Scantron, but we don't have to, know all the answers. A lot of the answers are provided. We just need to be able to write A, B, C, D, E, or F. Okay, let's take a look at the next one here. So again, we have metal cans that are being seen as they pass through. So I'm giving the uncomfortable pause here in the case you were doing this at home. So this one, if we look at these as our options, then this one is going to be an inductive sensor. Okay, looking for the presence of metal. Okay, so I'll show each slide. There will be an uncomfortable pause where I have you try and figure out which type of sensor we're looking at here based on the options, and then we'll show the answer. So this one has a light beam going out. It looks like there is a transmitter and a receiver on the side. I'm looking for different pins on the pin header here, and if it's missing, then the light will actually go through to the receiver. So this one, based off of these options, our best answer would be the opposed sensing photoelectric sensor. Okay, let's take a look at the next one. Okay, so we have a sensor mounted on one side. Looks like we have a massive reflector on the other side here. So this one is a retroreflective sensor. So we don't have to look at the options. We know that a big-ass reflector on the one side there is telling us that is the retroreflective photoelectric sensor. Okay, let's take a look at this one. This one always trips people up. So it looks like we have these perfume bottles going through, and the top of the unit here has these, the sprayer on the top here. It has come off, and so this one doesn't seem to have a reflector. It's not looking for the presence of metal. A capacitive sensor would have to be way closer to look at this guy. So this is a photoelectric sensor. And out of the photoelectric sensor, there is no receiver on the other side. There is no reflector that we can see. So this is a diffused sensor. So normally the light would go, bounce off the cap, and come back to give us a count. And this one here, it won't be able to see because the light would hit this, this spray, and then the diffused light wouldn't be enough to come back and trip it off. So this one is an example of a diffused photoelectric sensor. Okay, next one. It looks like there is a red LED going out. So this one is looking for filling. Again, it's an LED, so it's a photoelectric sensor, but there is no receiver on the back end here. There is no reflector. So based off of these options right here, this again is going to be the diffused sensor. So be careful. If I put the same sensor side by each, then sometimes you think, oh, the last one was diffused, so there's no way that this one could be diffused. There's a little bit of mind games that I'm giving here. So you may have the same sensor on both questions. Okay, let's take a look at the next one. So we have wood going through, and it looks like it is blocking a number of light beams there. So with this one, it's not a diffuse sensor because we have a transmitter and a receiver. So this is a light curtain, and as it breaks a number of LEDs, then it tells you the size of the log going through. So this one has a transmitter and a receiver on the other side. So this one is the opposed sensing photoelectric sensor. Okay, let's take a look at the next one. We have beef patties coming through. Again, it looks like we have a red LED that's being punched out. So this could look at a number of different things. This could look at the fact that we have different beef patties coming through and giving us a count for each one. Or we could change the sensitivity of the unit so it could look at whether it's cooked or not cooked, right? Depending on the color, then we could change the sensitivity to have more or less light coming back. But this one is a light sensor. There is no reflector, there's no receiver on the other side. So again, this one looks like my favorite so far, the diffused photoelectric sensor. Okay, let's take a look at this guy. Again, we have a light sensor there. There is a a red LED that's being punched out there. I mean, oftentimes it's an infrared LED, but they're just denoting that it's an LED punching out a light. And this definitely seems to be my favorite because there doesn't seem to be a reflector on the other side of the conveyor. There is no receiver on the other side of the conveyor. So this is a diffuse sensor in that the light goes out, bounces off each of the boxes, and once enough light comes back to the receiver, then it changes the output. Okay, on all of these guys, if I failed to mention, then we're seeing that the sensor is mounted in the specific spot. So if it craps out, we just back off these two screws here, get another sensor, put it back in, and the connections for the wiring is done with a quick connect coupling. So you don't even have to worry about the wiring once it's already set up. You just basically, if that sensor crapped out, you would remove that sensor, put another sensor back in, reconnect the wire harness on the back end here, and be up and running as long as, in the amount of time that it took you to go get a new sensor. But this one is an example of, again, a diffuse photoelectric sensor. Okay, let's take a look at this guy right here. So it looks like it's very close to the unit or the target that it's looking for. And it's looking for, it looks like the presence of metal caps on the top here. So your choice for this guy, because it's so close, would be a capacitive or an inductive. And for this guy, we're looking for the presence of metal. So I would go with the inductive sensor. Okay, let's take a look at the next guy. So it looks like we have a sensor that's mounted on the side of a tank. It looks like it's looking at liquid level sensing there. So it's not looking for the presence of metal. There's no way that an LED would be able to punch through the opaque side of this unit. So given these options right here, this one is the capacitive sensor. So we would be able to reduce the sensitivity of the sensor so it no longer sees the tank wall, but is able to see inside the tank for liquid level sensing. We'll have a high and a low limit here probably. Okay, I'm starting to lose my voice, so that hopefully we're done soon. So let's take a look at the next one. So it looks like we're looking at little nibs coming through. I don't know what those guys are, but it looks like we're looking for a count of each of those little parts that are going through. Again, we're seeing a red LED being punched out. So it looks like this is the one where I've been able to grab the most pictures off of this sensor from the internet. So this again is a diffuse sensor. Remember that these guys could be going past so fast that we can't even see them. Remember that this switch is a transistor. It can switch thousands of times a second. Okay, so that one there is again a diffuse photoelectric sensor. And let's take a look at this guy right here. So this one looks like, so whenever you see these guys, this is a sound wave that's coming out. So we have a thing from IKEA coming through, and it looks like the ultrasonic sensor is mounted on the bottom to keep track of each piece that's going through there. So oftentimes you'll have a diffuse sensor or an ultrasonic, but we can see here that it's sending out a sound wave. So let's go with the ultrasonic sensor. Okay, 44. This is from the, what is this? This is from the Canada's Wonderland or whatever, like the amusement park. And so often with the amusement parks on all the rides, we're going to need to have redundancy. So we have 3 separate sensors, all giving us redundancy. And it looks like we're looking for the presence of the teeth here. And so they're very close to the actual target here. They're looking for the presence of metal. So this guy is most likely an inductive sensor. Okay, next one. Looks like we're looking at milk cartons or water bottles going through. Again, it looks like we have a transmitter and a receiver on the other side, a transmitter and a receiver on the other side. We can see that red LED, so we know it's a photoelectric sensor. So this one is the one where we have a receiver on the opposite side. So this is the opposed sensing photoelectric sensor. Okay, let's take a look at the next guy. Okay, so we're looking inside the pallets here, and we're looking for the presence of different materials there. Again, we could use a diffuse sensor, but it looks like what's being depicted here is a sound wave. So we have a sound wave going out, bouncing off the box and coming back. This is another sensor company, Pepler-Fuchs. And so that ultrasonic sensor is going down and coming back and telling us the presence of the box. Okay, so that one there is E, the ultrasonic sensor. Okay, let's take a look at 47. So this one here, we have a red LED going out. We're not sure whether this is retroreflective, diffuse, or opposed sensing, but we can just make out here that there is a reflector on the other side of the unit here. So this is probably a polarized retroreflective sensor. Okay, so 47 is D. Let's take a look at 48. Okay, 48 looks like we're having some machine, and it looks like there's a piece of sheet metal that's there, and at different travel points. Then we have a sensor that is sensing that piece of metal very close to that piece of metal there. So anytime that we're looking at a sheet metal piece where we're looking at the travel, this guy is going to be our inductive sensor. So 48 is F. Okay, next one. We're looking at different fabrics, or we're looking at a paper mill. And so the paper is having a dip here to reduce the tension on the line there. So again, we could use a diffuse sensor to look at this. We could also use an ultrasonic sensor. It looks like we are looking at an ultrasonic sound wave being depicted here. So let's go with the ultrasonic sensor. It's being used to look at probably an analog output here for the size of the actual roll. So when the roll is done, then the sensor will give a different output. And for this guy, we're probably looking for a static value coming out so that we know that there's, or like a certain range that's coming out from the 4 to 20 milliamp of the ultrasonic sensor to tell us that we have that dip, and we're not going to put too much tension on the fabric or on the paper there. So that one again is an ultrasonic sensor. Okay, number 50. Looks like we have a milling machine here, and so it's looking at different points there. You can see that the cam is right here for the different points of travel there. And so again, it has that quick connect coupling here. This one is looking for the presence of metal. So anytime you're looking for the presence of metal, then I would go with an inductive sensor as your answer there. All right, guys, so that is 50 questions on sensors. If you want, you can check out a couple of additional videos. So in class, I'm most likely showing you this one from 6 Sensors right here. I love the names that they give these companies. So 6 Sensors is another company that gives or makes sensors. So this is from 2009, but still shows all the different types of sensors that are being used out in the field. So right here we can see like a retroreflective sensor that's being used here. Looking at all the different palettes going through, that's a diffuse sensor on the bottom there. So I will most likely show this guy in class. And then if you're still interested in this stuff, then there's some pretty cool videos. And if you have other videos that you can find that are pretty cool on different warehouses that are out here. So this one here is the warehouse of the future. So this is from 2017. You can see here that they have different pallets with different units going through. And then these guys are often being, so you can see here there's a little pusher that goes, oh that's kind of cool, moves it over to the other side of the unit. So these guys are all being housed in this warehouse here where, excuse me, each part is being placed into different tray locations. And then they have these motors that go through with encoders to tell you exactly where you are in the unit there. So 2017 is basically the way that everything is being set up. A couple other videos here that are interesting. This is for tiles and stuff like that. So heavy loads, but essentially the same thing where they're all being placed into this vertical storage unit here to keep track of each different pallet as they go through. So still using the same type of sensors that we looked at for our review. But if you're still interested in cool things, then take a look at this video right here. So this is the auto store. It's really cool. It's this company called, what is this company called? Hatland Solutions. And basically what they have are these little robots. And let me go back just a touch here. And it looks like instead of having the vertical storage, they have a horizontal storage system. And so each of the pallets, or there's a name for this, but each of the boxes are being placed on one on top of the other. And so units that are being sold quickly and more often are going to be on the top. Other units are below there, but these little robots are able to pick up each of the boxes and then either store them in different points or bring them over to the human. And then watch this, it goes down here to the human, comes out, and then we could grab the box, put the label on it, put it in for the certain customer, and then it moves on. So this might be the way of the future in that it allows for quick and easy access of each of the different types of pallets going through. Again, not using the exact same sensors as we saw before, but who knows how things are going to revolutionize in our storage of all of our units here. Anyways, hopefully that helped in going through all the different types of sensors. If you have any issues or questions, then leave them in the comments below. And if you're in my class, then we have a week before the next test. So come and see me and I'll clear up any misconceptions on what we've talked about so far. All right, guys, thanks for your patience. We'll see you in the next video.